Hi, welcome to another lecture on Calculus 3. Today we are going to have a particularly short lecture on certain calculus type operations. These were related to limit, continuity, differentiation, and integration. Let's go ahead and see what the topic is about. So, uh, these are particularly simple because they are so-called component-wise operations. The following example is going to make it very clear. Suppose I have a vector valued function in 3 dimension is made out of 3 functions: sine of t over t, exponential of 2t minus 1 over 3t, and the third function is 1 minus cosine of t over t squared. So I could ask, for example, what's the limit of this function as r goes to 0? Of course, we cannot just plug 0 in these formulas because all of them lead to division by 0, and that is not well defined. So how do we find the answer? Simply, whatever we learned in calculus, we have to do it 3 times, and that's what component-wise refers to. So what was the sine of t over t when t goes to 0 in calculus 1 or in pre-calculus? Do you remember what that limit was? So there were certain tools you had, certain major theorems that were covered at the beginning of calculus 1. For example, do you remember what was the name of a major procedure to help us answer this type of question? If you said L'Hopital rule, you remember your calculus 1 very well. Or some other properties, for example, when it came to these type of functions, you could arrive at the answer in many ways. So sine of t over t when t goes to 0, that's just 1. Here you can apply L'Hopital rule. You see that the answer is 2/3. You can answer this by L'Hopital rule or Taylor series or something, and you see the answer is 1/2. So we just have to repeat our process multiple times. With respect to continuity, a vector valued function is continuous at a certain point if all the functions involved are continuous at that point. So if any of them fails to be continuous at a certain point, then the entire function will be discontinuous. For the derivative, if you want to take a derivative of a function, you simply differentiate all 3 functions that you have. You can write it in this notation, or you can write it with the notation of ijk. For example, we said f prime I, g prime j, and k prime, h prime, k. You remember I, j, k were are unit vectors, and in your text they're going to be shown with bold-faced notation. Probably the only item that is new in this section is the concept of a smooth vector valued function. What do we mean by that? Well, the concept of something being smooth is just what you think of it, something without kinks, without cusps, without corners and such. That's what we are trying to imitate here. How does it go? A function is called to be smooth on some interval if all 3 derivatives, f prime, g prime, h prime, they are all continuous on that interval, and all 3 of them do not turn out to be simultaneously 0. So this is the only condition that is significant here, is that r prime is not 0 at a certain point, and we have to go ahead and explain what does this condition mean. So if all of these conditions are met, that the 3 functions are continuous, the derivatives are continuous, and they are not 0 simultaneously, then we call the function to be smooth. If it so happens that r prime does become 0, the point at which this happens has a special name. We refer to it as nodes or cusps or a variety of other names. I'm going to go ahead and try to show you some examples of nodes or cusps later on, but let's go ahead and continue with our basic ideas here. We had differentiation rules in calculus 1. All of that continues to calculus 3 without any change at all. So for example, if you have a constant times a vector valued function and I want to differentiate, the constant just multiplies the derivative. So it's important for the c to be constant. If I have addition or subtraction of two vertical valued functions, I want to differentiate it. I simply differentiate each of them in add or subtract. What about the product rule? Product rule comes in three varieties depending on what you have in mind by a product. We can have a scalar times a vector. We can have a vector dotted with another vector. We can have a vector crossed with another vector. So long as you respect whatever multiplication you have in mind, the exact same rules of product rule that you had in calculus 1 still is applicable. We don't have anything new to report here. So if you have a one function times some other function you want to differentiate, product of the first times the second plus the first times the product of the second. If you are dotting two vector functions and you want to differentiate, still product of the first dot with the second and the first dot with the product of the second. So it's important that the type of multiplication that you have here will be the one that you started with. If you have two vector valued functions crossed with each other, when you want to differentiate, derivative of the first cross with the second plus the first cross derivative of the second. How about the chain rule? Again, no change here. If you have a function, a vector valued function whose argument has been replaced by some other scalar function, you want to differentiate, this is the derivative of interior function times derivative of your vector valued function calculated at the interior function. Perhaps the only other new item here is that if the dot product of a vector valued function with itself is constant, then dot product of that function and its derivative will be 0, for a simple fact that if I differentiate this thing, I'll get r prime r plus r prime, these are the same thing. The derivative of a constant will be 0, and therefore r dotted with r prime will be 0. Okay, so all of these rules are quite basic. Let me, the only thing to do is some exercises and explain perhaps what is the significance of this issue of derivative becoming 0. Let me show you some pictures and then perhaps some functions that go with it. One of the most famous functions that shows this behavior of having nodes or cusps is the so-called Brachistochrone. Brachistochrone has a very splendid history in mathematics, and perhaps I can convince you to go look it up in literature online. There are plenty of videos, interesting explanations for the thing, but here is an explanation of one of these curves and where it comes from. Suppose we take a circle. This could be a coin or could be a bicycle wheel or something. We take and put a colorful dot on some point on the rim of this, and then we take this circle and roll it on a line without skidding. While we do that, we are going to follow where this colorful dot's going to be. The colorful dot is going to go on a certain trajectory. That trajectory is referred to as Brachistochrone. That is that famous curve I've been talking about. So here is a little animation I made so you can see what happens. So I'm going to imitate taking this say bicycle wheel which has this red dot on it, and as this bicycle wheel rolls on this line, let's see what happens. So that dotted line on the rim goes on this particular curve. At that point, that's where the cusp is. That's the cusp or the node where the derivative of our vector valued function becomes 0. It's right that point, and then this thing repeats itself over and over again. So well, we are trying to explain what cusp is. Well, this thing looks like a cusp. Here's a cusp. Yeah, and what's the significance of it? Well, that's where a certain motion momentarily stops. Okay, imagine like a car on a road just stopping, all of a sudden stopping. Once you stop, you can, well, make a U-turn, K-turn, or turn around, or whatever. But while you are traveling, your next location will be predictable, but once you stop, it's no longer predictable. So now, before we move on to actual problem that leads to this thing, why is this so famous in mathematics? One of the first times that the curve showed up was in a challenge problem by a famous mathematician by Bernoulli, and his question was the following: if I want to go from one point to another point on a slide, so I want to make a slide that takes me from point A to point B. I'm sliding without friction or anything. The question is, what shape of a slide is going to let me go from A to B in the shortest amount of time? So many people had guesses about this thing. One of the more famous guesses was by Galileo, who thought a circular arc is going to be the best. It turned out to be a good approximation, but not the correct answer. So many famous mathematicians worked on this problem, including Isaac Newton and Bernoulli brothers. All of them worked on this, and at the end, the correct answer turns out to be exactly this, with this particular name of Brachistochrone. It shows up in many places, and this is the first appearance of this curve. Here's another example of the same thing. This is a similar curve made in 3 dimension, and that one also exhibits this behavior of having a corner in it. So when we are talking about the smooth functions, we are avoiding these corners. So from one corner to another corner, to next corner, our curves are going to be considered smooth, and at these cusps, we essentially end up separating our functions into pieces and analyzing them like that. So here is a particular problem statement itself in the text. It says, suppose r of theta is given as say theta plus sine of theta times I plus 1 minus cosine of theta times j, and it is asking you to find intervals on which the given function is smooth. So it doesn't have those peculiar looking corners and such. Well, we have to find r prime. R prime differentiation is straightforward. 1 plus cosine of theta times I. Derivative of this one is minus sine of theta times j. And then the function is going to stop being smooth if all of the components become 0. So this one we set is equal to 0, this one sets equal to 0. So this one tells me that cosine of theta is equal to minus 1, while this one is just what it just told me. So theta when does theta become 0? Well, 0, pi, 2 pi, 3 pi, any multiple of pi, sine of theta becomes 0. How about when does it cosine become minus 1? Well, cosine becomes minus 1 if you are at pi, then you have to go around a circle, come back, and then now you are 3 pi, and then 5 pi, 5 pi. Essentially any odd multiple of pi. Well, what's common to both of them? We want them to be simultaneously 0. We're not collecting all of this and all of that. Rather, what is common? Well, what is common is at pi they became 0, at 3 pi they became 0, and so on. So we say R is not smooth at odd multiples of pi. So that would be pi, 3 pi, minus pi, and so on. So R is smooth from, say, 0 to pi, everything's okay. Then from pi to 3 pi, again, it's okay. So the other side of the coin is to single out where it is smooth, meaning you have not reached those particular corners. Okay, so many questions on this section are all straightforward: addition, subtraction, multiplication, division, differentiation, or integration. I forgot to give any statement about integration, but again, if you want to integrate R, let me write it here. It's simply integral of f, integral of g, integral of h, each of them having its own separate constant. So C1, C2, C3, or however you want to name your constants, they each inherit a separate constant. Okay, this is going to be one of the simplest sections that we have, and so perhaps one of the sweetest in that regard. Let's prepare for the next lecture, which is going to be on velocity and acceleration on three-dimensional curves. Until then, good luck and God bless.